All right, friends, so in this video, we're going to be talking about similarity, so similar figures, similar polygons, similar triangles, and then a little bit of proportions. So just to kind of get us started, talking about what similarity means, what it means for two figures to be similar. Two figures are similar if two things happen. One is that all corresponding angles must be congruent, and the other is that all corresponding sides are proportional. And both of those things have to be true. All corresponding angles have to be congruent, and all corresponding sides have to be proportional. And that's what it means to be similar. So eventually, in a minute, we're going to talk about how to prove similarity. But to start off with, if I happen to know that two polygons are similar, right, then I can use this information. I can say that my sides are proportional, or I can say that my angles are congruent. Okay. So for similar polygons, the ratio of corresponding side lengths is equal. That's really the same thing as saying they're proportional. If I make a ratio of corresponding sides, that ratio is going to be the same for any pair of corresponding sides. So here's an example problem. I've got a triangle, and its sides are length 10, 12, and 14. Now I want a similar triangle whose perimeter is 72. Now, interestingly here, right, they didn't tell me any of the individual sides of this other triangle, this larger triangle. They only told me the perimeter. But if you remember, when the corresponding side lengths all have equal ratios, the perimeter, the ratio of the perimeters is also equal. It's going to be that same ratio. So what I can do here is say, okay, well, if this guy's perimeter is 72, I can find this guy's perimeter. So the perimeter here is going to be 10 plus 12 plus 14, so it's going to be 36. And the ratio of the two perimeters is also going to be equal to the ratio of the corresponding sides. Now, which sides do I want? Well, it tells me that I want the shortest side of this larger triangle. And so that's going to correspond to the shorter side of this smaller triangle, which is my 10. Now, I do want to be careful here. I have 36 over 72, so I do have the smaller triangle on top, the bigger triangle on the bottom. So that means that 10 is going to go on top because it's from my smaller triangle. And the piece I'm looking for, which we'll call x, is going to go on the bottom. And now I've got a proportion to solve. Now, you can do this without simplifying first, or you can simplify first. Personally, I like to simplify first in a fraction if I can, because oftentimes I won't be using a calculator for these kinds of things, and using smaller numbers tends to help. So what I'm going to do is I'm going to say 36 over 72. I can reduce that. That reduces to just 1/2. And now I have smaller numbers to work with. And of course, to solve a proportion, what we're going to do here is just cross multiply. I've got 1 times x is going to be equal to 2 times 10. So x is equal to 20. That's that missing side that we were looking for. Okay. In this case here, I was told that ABCD is similar to PQRS, so I have two quadrilaterals that are similar. Okay. Now here they didn't tell me necessarily straight out which pieces correspond, but they actually did, because if you recall, when I'm given a similarity statement like this, the order of the letters tells me which pieces correspond. So for example, if I'm looking for AB, right, that's got an X in it, that's one of the things that I'm looking for. AB is going to correspond to PQ, and I know that because AB is the first two letters in this quadrilateral, and PQ is the first two letters of that second quadrilateral. So I know that those pieces correspond. And similarly, if BC is the other piece that I'm looking for, because those are the middle two letters, that's going to correspond to QR in my second quadrilateral. And then I can go ahead and just plug in the pieces that I know. So AB is X, BC is X plus 8, PQ is 2, and QR is 6. And again, I can just solve this by cross multiplying. So I've got 6 times X is equal to 2 times X plus 8. And then we're just doing a little bit of algebra to finish up here. I'm going to distribute that 2 through. Subtract the 2x to get all of my variables on the same side. And then finally divide by 4. to get the variable that I'm looking for. Okay, so next up, I want to talk briefly about the triangle proportionality theorem. That says that if I've got a triangle and I have one side inside of it that is parallel to one of the sides of the triangle, then what I've done in some ways, well, what I've done is created similar triangles. And the triangle proportionality theorem then says that the way these two sides that are split up makes proportions. So I could say A over B equals C over D, the way that I've simplified or labeled this here. Okay, and I know we didn't talk too much about properties of proportions, but one of the interesting things here is that, yes, I've written A over B equals C over D, right? So I've kind of written it as like top over bottom equals top over bottom. That's not the only correct way of doing it. All of like this proportion would be just as correct if I wrote, say, A over C equals B over D. So there are a lot of good correct proportions that you can write from here. You just want to have some kind of sort of organizing principle, right? So the way I have it written is like top over bottom, right? You could choose to write left over right or right over left or bottom over top. As long as you're keeping that consistent rule for yourself, you're very likely to get a proportion that is correct. Okay. Here's an example problem with this. So here I've got BD is parallel to AE, so I know that this rule applies. I've got AB is equal to 6, that's this little bit down here. BC is 15, DE is 4, and then I'm looking for CE. Now CE is interesting because CE is this whole thing. That's the piece I'm looking for. Okay. So if a thing I'm looking for is CE the whole, right? I could do something like x over 4. And then my kind of organizing principle here is the whole over the bottom. And then I want to make sure that my other fraction that I'm writing then is also the whole over the bottom. So I need to know what the whole thing is here. Well, that would just be 6 plus 15, so 21. Over the bottom piece here would be 6, right? So there's a correct proportion we could write. And then we'll solve from here, right? So I've got 6 times x is equal to 4 times 21, which will be 84. Divide both sides by 6. And x is, let's see, 6 goes into 8 one time, with 2 left over. 6 goes into 24 4 times, so x would be 14. Okay. Now keep in mind that is one correct way of getting to this answer. If you didn't like calling that, the whole over the bottom, we could instead have, say, solved for CD, right? And done y over 4 equals 15 over 6. And then just added whatever I got for y to 4 at the end to figure out what CE is. That would be another correct way of doing this problem. So as long as you're getting 14 for CE, even if your work in between looks different, that's okay. Now, next, I want to talk about similar proofs. Okay. Now, quadrilaterals and anything a little bit more complicated definitely is further than we got in this class. We talked about similar triangles. So I do want to note that we only proved similarity in triangles. Okay, but if you remember, there were actually 3 ways or 3 methods that we used to prove similar triangles, right? One of them was angle, angle. One of them was side, angle, side. And one of them was side, side, side. And the important thing to remember that's different between similarity and congruence, right, which were the other types of proofs that we did, is that in similar triangles, yes, the angles should be congruent, right? So angle, angle means I need 2 pairs of congruent angles. But when we've got sides going on, I don't want those sides to be congruent. I just need them to be proportional. So this means a pair of congruent angles. And then 4 sides that are in proportion, right? But that's actually just one proportion. And that's all I need to use side angle side similarity. One pair of congruent angles and one true proportion with sides. Because you'll notice if I've got, one proportion with sides, what's going to happen is you're going to get 4 sides in there, right? 1, 2, 3, 4. That's the 4 sides that I need, okay? Now, it is important to note, right, that side angle side, the angle that I know, does have to be in between the 2 pairs of sides. Okay, so just make sure you're remembering that. And then finally for side, again, I need 6 sides, but what does that look like in a proportion? Well, that would be like just adding a third fraction onto here, essentially. Right? That gives me 6 sides. So essentially for side, I just need one like extended proportion, if you will, one proportion that's got 3 fractions in it. Okay, so those are my 3 methods: angle, angle, side, angle, side, and side, side, side. And you'll see one in a second. Okay. The thing also to remember with similarity proofs is once I prove that triangles are similar, then I can go on to say one of 2 different things, right? Going back to that definition of similarity, right? So I can either say that corresponding angles of similar figures are congruent, right? Angles are congruent. Or I can say corresponding sides of similar figures are proportional. Right? So these are the 2 pieces that can come after similarity. And then if you want to go one step further beyond that too, if I happen to have a proportion, right, then I could cross multiply, or I could use that property pom equals po, right? Product of the means equals product of the extremes. To actually get a product of 2 sides is equal to a product of another 2 sides. So if you see like this example here, the thing that I'm looking for, that's going to require me to make a proportion and then use pom equals po. So here's an example of how a similarity proof works. I've got these 2 triangles in this figure. I have RS is parallel to TW, and I want to prove that statement. 2 sides multiplied together is equal to another 2 sides. So let's get ready here. We'll make a statements and reasons column and get going. So now we always start with the given information. So I'm going to start with RS is parallel to TW. And I know that because it was given. I'm marking up my picture here, RS and TW. Okay. And what I'm noticing here is that RS and TW, because they're parallel, I'm seeing a Z shape. And I know that when I've got parallel lines and they make a Z shape, I've got alternate interior angles. And I can say that those angles are congruent to one another. So I can say that angle S is congruent to angle T. Because if lines are parallel, or lines are parallel if and only if, alternate interior angles are congruent. Similarly, I have another Z shape happening up here. And so in the same statement even, I can say that angle R is congruent to angle W for the exact same reason. And that's all I need to go ahead and prove my 2 triangles are similar. Now keep in mind too, I know some of you probably noticed that I have vertical angles here, right? SJR and TJW. You absolutely could have used those in your proof as well. I just happen to know that I only need 2 pairs of angles to be congruent, and I've got my 2 here. So I'm going to leave that out for now, but if you wanted to use one of these pairs of angles and the vertical angles, that would work perfectly well as well. All right, so being careful of the order of the letters, if I go S, R, J from my angle marked once to my angle marked twice, that's similar to once to twice, so T, W, J. Those are similar by angle, angle. Okay. And then again, where can I go from here? Well, I want to say sides. I want to talk about sides. So I know that when I've got similarity, my sides are going to be proportional. So I've got RS and TJ. And because those guys are going to be multiplied together, I know that they actually need to be diagonal from one another in my proportion, because that's how I'm going to get them to be multiplied together in the next step. And for the same reason, TW and SJ also have to be here, have to be on diagonals like this. Now, I do want to make sure that my pieces that correspond are together in the same fraction. So RS in this triangle corresponds to TW here. That's how I know that TW goes on the bottom, and then SJ is going to go up top here. Okay. The reason for 4, again, is exactly what we said before. Corresponding sides of similar figures or similar triangles are proportional. And then I know that I can cross multiply because the product of the means equals the product of the extremes. POM equals PO. And that's a similarity proof. One more quick thing for us to talk about today, which is just solving proportions. And this really takes, again, us back to that idea of product of the means equals product of the extremes, or cross multiplying. Now, we've solved a couple of proportions already in this video, so I'm going to let you do number 1 on your own. Number 1 is nice and straightforward. Number 2 is a little bit more interesting for a couple of reasons. So let's do number 2 together. First up, you'll notice that it doesn't really look like a proportion because I only have a fraction on one side. I don't have a fraction on the other. Remember that if I only have a fraction on one side, I can rewrite this guy on the left as a fraction by putting it over 1. And now I can go ahead and cross multiply. So I've got k minus 1 times k minus 4 is equal to 1 times 4. Now over here, I've got a binomial times a binomial, so I'm going to need to double distribute or FOIL. K times k is k squared minus 4k minus 1k, and then negative 1 times negative 4 is positive 4. And then getting some like terms together. So k squared minus 5k plus 4 equals 4. Now this is a quadratic equation because it's got a square in it. That's why it's a little different from the other equations we've seen in this video. If you remember, the strategy for solving quadratic equations is I want to get everything on one side of the equation first, and then I can decide which method I want to use. Okay. So doing that, I've got k squared minus 5k equals 0. And of course, when I'm solving a quadratic, the first method I want to try to use to solve is factoring. Can I factor this? Okay. In this case, I can. I can take out a GCF. Okay. I can take out a factor of k. So if I pull out a factor of k, then I've got k minus 5 left. And then once I've got a product of two things equals 0, then I know that one of those things must be 0. So either k equals 0, and that's one solution, or k minus 5 equals 0. And so if I just add 5 to both sides, k equals 5 is my other solution. So this particular proportion actually has 2 different values of k that will make it true, which is interesting. That's it for this video, guys. Thanks for hanging in there with me, and I will see you in class.